Hey, what's up? It's your old pal, Mr. Cook. We're going to work on this Unit 7, Part 1 test review. Okay, so for the first video we're going to go ahead and go through the methods of figuring out which test to use, and then we'll do the tests, in separate videos. So this one is just going to be about like determining which test to do. Okay. All right. So when I think about like what test to do, I first need to get familiar with which tests I have to choose from, right? Well, on the test, right, you're going to be able to use your calculator and also this little summary of all the tests for the series. You'll be able to use that on the test as well. Just because, like your goal is to memorize how to do these tests for the AP test, but, like you can, for our test, we just want to make sure you know how to use them properly and figure out which one to use. So usually like I go in this order. I kind of like look for, the easiest route. So I always think about nth term test always. So usually like I'll go through the problem and look at the sequence. And if I know that the sequence, as the sequence terms get really, really big, it doesn't go to zero, I automatically think that it's going to be divergence. Then I look for the ones that have really obvious characteristics, like a geometric series or a P series or an alternating series, because I'll have that little -1 to the power of n, or ratio test, because root test, because it'll have like a power of n on it. Then I go to some of the other ones. So that's like my first kind of round, nth term test. And then my second round is going through the ones that like have distinct characteristics. And then after that, I kind of go into a deep dive, like with integral test. Does it look like kind of problem that like I wouldn't be able to solve any other way unless I integrated a couple of times? And with the ratio test, it's usually like a combination of some of these, like the roots or alternating series, but predominantly like geometric series or factorials and stuff. And then the other really obvious one are these two, where it's like if it looks real close to one of these ones, like a P series or a geometric series, I usually use the limit comparison test for that one. And I usually use this one, the limit comparison test, where you make a fraction instead of direct comparison. And they are more or less interchangeable. I can't really think of any examples off the top of my head where you could use one instead of the other. But I do know that limit comparison is a lot easier to use because you just need to think about something that looks like that sequence, and then you just got to show that they end up becoming like some value if you make a fraction out of them. So remember that it's interchangeable so long as the number is greater than 0, you're good. So you can like put one sequence on top of the other. Whatever. We'll get to that when we get to that video. Okay. But yeah, so you'll have this list, and now I'm going to go through like the way that I kind of look at the problem and make an initial judgment call as to what test I'm going to use. Like number 1, that's a real obvious one to me. It's got a power of n on it. And then inside of the exponent, there's like a function. If it was just a constant to the power of n, I would say, hey, that's probably geometric. But this one looks like it's going to be the nth root test. So root test for this one because of that nth power. Okay. And then number 2, oh yeah, this is geometric all the way. So I would just rewrite this thing, n equals 1 to infinity. And that 8 over n over 5 over n, 5 to the n, I can just rewrite that as one, exponent. Of course, and also because the exponent powers are the same, but if they were different from each other, like one of them was 8 to the n plus 1 over 5 to the n or whatever, then I would just rewrite this as, 8 to the n plus 1 is really 8 times 8 to the n, because like since they have the same base, you'd multiply them and you'd add the exponent powers together, so it gets n plus 1. So this would allow me to pull an 8 out, and then it'd still be a geometric series. But this is even better because it's just 8 to the n and 5 to the n, so it's real easy to just turn it into that. But it's easy to spot geometric series. Even number 3, like that's a geometric series, but it's off by a little bit, right? Whenever it's off by a little bit, think about using a comparison test. So I am going to use limit comparison test for this one. And then I'm going to compare it to a real similar series, a geometric series that looks like this. All I do is take that -1 out of it instead of 4 to the n and then -1. It'll just be 3 to the n over 4 to the n, which then turns into this geometric series, 3 over 4 to the power of n. And that's like what I would compare it to. So I'm going to use geometric series for this one to show that it's going to be either convergent or divergent. So like, remember that limit comparison test, you always have to use another convergence divergence test on the series that you're trying to compare it to. Next, let's see what we got here. N over natural log of n. What would I do with that one? Let's see. I mean, I'd first think about nth term test. So I'd like, just consider it nth term test. I'm not really 100% sure. And then I'd like real quickly just check the limit on this thing. So I'd check the limit as n goes to infinity, n over natural log of n. And let's see here, as n goes to infinity for the top part, well, as n goes to infinity for just n, that goes to infinity, obviously. And then as natural log of n goes to infinity. So yeah, that would also go to infinity. So I could use L'Hopital's rule for this one. So I'd rewrite it as limit as n goes to infinity of, and the derivative of n is just 1. Derivative of natural log of n is 1 over n. And then if I, multiply by the reciprocal there, then I get n. So limit as n goes to infinity of regular old n. And this will go to infinity. So yeah, obviously this thing is going to diverge. So, if I see an nth term test, I'll just write it out if I think it might be nth term, because that's real quick to see if it's going to be divergent or not. This diverges. Okay. So yeah, that one ended up being nth term test. Maybe I'll do that in this video. If I see something that I think might be nth term, I'll test it out and real quick see if it's going to diverge or not. This one, oh man, this is like textbook ratio test because it's got a factorial and also an exponent in it. So ratio test all the way for this one. I use ratio test whenever there's like a combination of a geometric series or an exponential function and a factorial or a polynomial. Like it's when you have combinations of the two, that's when I think to do ratio test. This one, if I got rid of that +1 right over there, this would be 1 over 5 to the n. And I can rewrite that one as a geometric series. So you know what? I'm going to use comparison test on this. That's going to be 1/5 to the n. So I'm going to do limit comparison test here. And I'm going to use a geometric series test here to show that it's either going to be convergent or divergent. So yeah, that's geometric series all the way. And this is a limit comparison. So we'll come back around to that. Let's see, 4n over 2n squared plus 1. Oh, I'd probably use limit comparison test here. Here's why. That +1, I don't really need it, any addition, subtraction, all that stuff. Just ignore it, So if I just have this 4 over n, or 4 to the n over 2n squared, right? I mean, even if I just ignored the constants, those multipliers, I would really just have it as n over n squared, right? Like that's like really what we're looking at. That's the function of n that I'm interested in. And so, yeah, I'm going to use a comparison on this because if I simplify this a little bit more, watch what it turns into. N over n squared is really 1 over n. That's p series. So I'm going to use limit comparison test for this one, and I'm going to compare it with a p series. Okay, yeah, that's what's going to work real nice there. You know what? Same thing here. This would be a p series, not a limit comparison test. Because if I move that 2 out to the front, check it out. It's just 1 over n squared. Because you can take multiples out. That's why I kind of just ignored that 4 there and that 2 right there. Because multiples don't really matter. You can just kind of get rid of them, from the beginning. So anyways, so yeah, this is going to be a p series for sure. And that'll determine convergence or divergence. Okay, and then if I look at number 9, determine whether the series is convergent or divergent again. I would just use what I did over here, with just comparing like the main parts, those ones, and I'd like to see what happens. Well, if I compare the main parts right there, end of the third and end of the third, hey, something happens here. Okay, so I'm going to evaluate this thing with nth term test. because like when I was just looking at that, like, you know, the 2 n to the third over n to the third, if like, you know, I divide out the end of the thirds, this thing goes to 2. So in other words, the limit of this thing goes to 2. So I think nth term test is going to work real well here. So if I take the limit as n goes to infinity of 2 n to the third over n to the third plus 4, right? As n gets real big, you know, we learned that rule in honors algebra 2, where if the degree in the top is the same as the degree in the bottom, we just compare the lead coefficients. So this thing is just going to go to 2. So since it goes to 2, that means that by the nth term test for divergence, this thing is going to diverge. So there you go. There's an nth term test problem. Okay, what about this one? Oh, hey, this is another real fast one that I can check. Just check this out. It looks like an alternating series, right? But the deal is that, you know, even though it has that alternating part to it, the part that alternates, it goes to, you know, something other than 0. So that means that this thing is going to be nth term test as well. So I might as well do this one as well. So like, you know, I know that you're probably thinking to yourself, oh, why didn't I use alternating series? Well, let's say that you started with alternating series. The very first thing it asks you to do is to take the sequence that you're using. So 5n minus 1 over 4n plus 1. And you check what happens as, you know, the terms get really, really big, okay? And watch what happens. Again, just like the previous problem, number 9, the degree in the top and the degree in the bottom are the same. So we compare the lead coefficients, it goes to 5/4, which is not 0. So that means technically this thing would diverge because it fails the very first, you know, condition of alternating series test. That means that it's actually nth term test, and this thing diverges. So there you go, 9 and 10, real quick. Number 11, I would just move that 5 out front, and then it becomes geometric series. That's pretty easy. Right, I can just rewrite that 2/3 to the n. So geometric series test for this one. Pretty easy. Number 12. Oh man, that one looks crazy. Yeah, I mean, it doesn't have power of n, doesn't have factorials and exponents, doesn't have like much of anything, does it? My gosh. So, I mean, you know what I would probably do here? I would just like plug in a couple of terms and see what happens with this thing. This is a weird one. So if I plug in 1 for n, I would get the sine of 2 minus 1 times pi over 2. So 2 minus 1 is 1, so that's pi halves. And then plus my next term, if I plug in 2, I'd get sine of, let's see here, 2 times 2 is 4. 4 minus 1 is 3, so 3 pi over 2 plus, and then it would be sine of, let's see, if I plug in 3, 3 times 2 is 6, 6 minus 1 is 5, so 5 pi over 2. Oh, I see a pattern forming here. Okay, so then the next one's going to be sine of 7 pi over 2 and so on. So sine of pi halves is just 1. Sine of 3 pi halves on my unit circle is -1. Sine of 5 pi halves is 1 again. Sine of 7 pi halves is -1 again. Oh, you know what? Can you see it? This is just the same as saying, you know, the series n equals 1 to infinity of -1 to the power of n. And so that's what this is going to be, right? -1 to n minus 1 or plus 1, actually, just to make it line up. But this is just geometric one, you know, any way you look at it. So geometric series. That was a tricky one because you had to kind of like see what the terms turn into to see that it's a geometric series. That's tricky. That's real tricky. 13, determine whether the series converges to diverges. Okay. 1 over 5 to the n. Yeah, that's a real simple geometric series again. N equals 1 to infinity. 1 over 5 to the power of n. Geometric. Okay, and then after that, 14. Oh, I'd probably do a comparison test with this one because, like, The n is the only thing that really matters down there, so it'd be like comparing it to n equals 1 to infinity of 1 over n. And so that'd be limit comparison test. And then that's a p-series to show if it's convergent or divergent. So that's what I would use here. And then let's see. Natural log of n over n squared. Oh gosh. Yeah, what would I use for that one? Well, it'd be infinity over infinity. You know what? I'd probably test for an nth term test first. See what happens with that. So let's see here. Limit as n goes to infinity. And then let's see, of natural log of n over n squared. Okay. So then let's see the top part. That becomes limit as n goes to infinity of natural log of n. So that'll go to infinity. And then the bottom part, that'd be limit as n goes to infinity of n squared. That also goes to infinity. So then I'd use L'Hopital's rule for this one. So I'd get limit as n goes to infinity of, and then let's see, that'd be natural log of n. That's derivative 1 over n. And then n squared, that becomes 2n. So then that is, let's see here, 1 over 2n squared, which goes to 0, darn it. Okay, so it's not nth term test for divergence, but I'd like check it real quick. Okay, and then like the next thing that I'd try to do, let's see here. So those both go to infinity. I'd probably, like from here, maybe I'd check to see if this was integral test. So I'd probably investigate that one a little bit more. But first impression tells me it's probably integral test. But we'll look at it a little bit later, I'm sure. Because that's not like the nicest integral. Because I think I'd have to use integration by parts on that one. So we'll see. We'll see what it turns into. So that one's a little bit tricky. I don't know, just off first impression. 16 n over n squared. Let's see if I've got an n and an n squared. I'd compare it to this series because that plus 1 really doesn't matter. So I'd compare this to, let's see, n over n squared turns into 1 over n. So this would be a p-series. So I'd use limit comparison test on this one and then p-series. Okay. And then 17, determine whether the series converges or diverges. Well, this is real obvious. This is a geometric series. A lot of geometric series on this one. Maybe I'll just do like a quick video for those ones, like just by themselves. But oh yeah, and then this is a real obvious one. This is an nth term test for divergence. A lot of nth term tests as well, because like watch what happens as the limit goes to infinity. You can probably already see the degree in the top is the same as the bottom. It goes to something other than the 0. So this is the nth term test for divergence. Okay, so yeah, since the degree in the top and the degree in the bottom are the same, compare the coefficients, and it just goes to 5, which is not 0, and therefore this thing will diverge by the nth term test for divergence. Man, we're really getting through this. 19. 9 to the n over n to the fifth, so that's an exponent, and then also just a polynomial. Since it's a combination of the two of them, I bet you anything this is going to be ratio test. I'm very confident that it's going to be ratio test. So ratio test for that one. 5 over n to the 0.4, that's real obvious. That one's a p-series as well, because I can just rewrite this with the 5 out front, and then it looks a lot better, right? Looks 1. So 1 over n to the 0.4. Okay, and then 21. Well, yeah, we've got that power of n right there. This is going to be the root test. Because we have a power of n and then a function inside. 22, let's see. Oh, this is kind of tricky because you think it's alternating series because of that -1, but it's not. You can just rewrite it. So I'd just rewrite this as n equals 1 to infinity of -1 to the power of n over 3 to the n. And then I can rewrite that as, oops, don't forget the little sigma there. There we go. Then it's -1/3 to the power of n. So yeah, geometric series for this one all the way. All right, and then Determine whether the series converges absolutely conditionally or if it diverges. So yeah, this one it looks like it's an alternating series. Um, so yeah, I mean, I would do alternating series tests for this one first to see if it converges. And if it does converge, then I got to see if it converges absolutely or conditionally. So I just compare that to, I just look at the same thing without the alternating part. And you can do, you know, you can do this part first where you check to see if it's convergent or divergent first. And then go over here and see if it converges or diverges. Or if you wanted to, you could check this one first as well. And, because then you can see if it's going to be conditionally convergent or absolutely convergent right off the bat. I like to go in this way because then you can just stop at divergence. That's like my personal belief that you can stop there. But you can also just check this one first if you want. In my video, I'm going to check this part first. Okay. And then after that, I'll check the other one. But this one I'm going to be able to use probably, let's see here, if it's 1 over n factorial, I think I can use ratio tests on this one. But, I'll mess around with it when I work on it. But yeah, ratio test could work there, probably for sure. Now let's see, absolute conditional or divergence. Again, you can check alternating series tests for this one to see if it ends up working out. And yeah, oops, sorry about that. I don't know why I'm skipping around like that. But alternating series tests, and then you can check the 1 over square root of n. Now, square root of n, that's going to be n to the 1/2 power, right? So this just ends up being a p series on this part, for your conditional convergence or absolute convergence. And again, you can do this one first, or you can do this one first. It doesn't really matter which order you go in because you got to test them. Okay, and then 25, it's another alternating series. So I'd use that first alternating series test and check if it converges or diverges first. And if it converges, then I check for conditional or absolute convergence. So that would be n squared over n plus 1 squared. N equals 1 to infinity. So this one I do, let's see here, probably, that would be a nice one for nth term test for divergence. So nth term test to see if that one works or not. Yeah, because that one's not going to go to 0, so that'll be divergent anyways. Okay, 26. Determine the minimum number of terms required to approximate the sum of the series. So this is like error. So I'll do number 26, and do we have a 27? No, I'll do number 26 in its own separate video. Okay, so that's it for this one, just determining which method to go with, and then we'll make a video going over all those. Starting now. Okay, so we'll do like the first page and all that kind of in order. Okay, I hope you found this video helpful. If it's still a little confusing, hey, go talk to your teacher, get some help from them. They're not going to get mad or anything. They'll be welcoming to help you out. But that's it. So I hope you found the video helpful, and I'll see you in the next one. Bye-bye.